Question 6 is about the trace on an oscilloscope. And before we start this, it's important to remember that even though it looks like a wave shape, and even it does call it a waveform, you've got to remember that this isn't really a wave. It doesn't have a wavelength. What it is it's a graph of voltage up the side and time on the horizontal axis. So some people got confused because they were treating it as if it had a wavelength, and some people even tried to use the speed of light as being the speed of that wave. It's nothing to do with that at all. So the first thing we've got to do, we've got to calculate the frequency. So let's look at the information that's given. It tells us that the time base of the oscilloscope is set to 1.5 milliseconds per division, and the Y gain and 1.5 volts per division. I must say that 1.5 milliseconds, that seems a bit contrived, because I don't think I've ever seen an oscilloscope that has a setting like that. But let's not worry too much about that, let's just get on with answering the question. So, calculate the frequency. Well, the frequency is how many cycles do we get in 1 second. So if we look at the graph, often in questions like this, what we'd do is we'd look at one complete cycle. But if we look at one complete cycle, it starts there and it finishes there, which is quite awkward because we don't know exactly how many squares it takes to do a cycle. I suppose you could get a ruler and measure that and work out what fraction it was, but there is something easier. Instead of working on one cycle, which is awkward, if we look at what's drawn here, we've got 1.5 cycles, and 1.5 cycles does fit exactly onto a whole number of squares. And if we count across, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares is 1.5 cycles. So let's not worry too much about using formulas, let's write down what we know. So 1.5 cycles takes 10 divisions. So if we wanted to, we could work out that one cycle would take 2/3 of that, but it would be easier not to bother with that, because what we can do is we can look at the time base. It's 1.5 milliseconds per division. So 1.5 cycles takes 10 times 1.5 equals 15 milliseconds. And if 1.5 cycles takes 15 milliseconds, then one cycle takes 15 divided by 1.5 is 10 milliseconds. So the frequency the number of cycles you get in a second, if one cycle takes 10 milliseconds, the number that you get in a second will be 1 second divided by 10 milliseconds. So I could write 1,000 milliseconds, because that's a second, divided by 10 milliseconds. Or I could write 1, which is 1 second. And instead of dividing by 10 milliseconds is 0.010 seconds. So either way, whether I put 1,000 milliseconds divided by 10 milliseconds, whether I put 1 second divided by 0.010, I'll still get 100 Hertz as my answer. So notice for this, I haven't really used a formula. What I've done is I've just argued it through. I've kept track of things, what I'm counting, and how many of them have to fit into a second. I find that much easier than just looking up a formula. Calculate the peak voltage. So again we come back to the trace. It tells us that the Y gain is set to 1.5 volts per division. So to find the peak voltage, it's measured from the middle. So there's the middle, we go up 2 squares. So V peak is 2 squares times 1.5 volts for each square. So the answer is 3.0 volts. Calculate the RMS voltage. It's very straightforward, because either by having learnt it or by looking at the data sheet formula for alternating current, VRMS, is V peak divided by root 2. Yes, I've called that V naught, and earlier I called it V peak. Should have used V naught earlier, really, never mind. So it's 3.0 divided by root 2, which comes out as 2.1 volts. And the last part, state and explain the effect on the oscilloscope trace if the time base is switched off. Well, the time base is the thing that causes the dot to move across the screen. The applied voltage is the thing that causes the dot to move up and down. So if we turn off the thing that causes the dot to move across the screen, the dot won't move across the screen. But the voltage will still cause the dot to move up and down. So what we would get is we'd get the dot moving up and down, but not moving across. So you get a vertical line in the middle of the screen, or somewhere on the screen, depends how you've adjusted it, but you get a vertical line on the screen. And 2 marks are available, so to make sure we get both marks, as well as saying you get a vertical line, we could say how long the vertical line will be. And the voltage is still going to vary between plus 3 volts and minus 3 volts. So what you would see would be a vertical line that goes between plus 3 volts and minus 3 volts.